NASA is working on revolutionary propulsion technology that will enable us to reach Alpha Centauri in just 40 years. Currently, however, the dream of interstellar travel still seems like an impossible wish, thwarted by the vast distances of space. But in the future, the Sunbeam propulsion system is expected to accelerate a research probe to 10% of the speed of light, bringing it within reach of previously unattainable star systems. But how does it work? What technical tricks will make the endless vastness of space a thing of the past? And will trips to distant stars and exoplanets soon be part of our everyday lives? Be sure to stay tuned until the end and see for yourself the groundbreaking concept NASA is using to usher in the era of interstellar space travel. It's news that couldn't be more spectacular. The James Webb Telescope has recently confirmed that dimethyl sulfide actually exists in the atmosphere of the exoplanet K2-18b, a molecule that is produced exclusively by organisms on Earth. This is by far the strongest evidence of extraterrestrial life found to date. And according to experts, the oceans of this alien water world could even be teeming with life. Now imagine that we could send a research probe to K2-18b that would conclusively confirm the existence of our long-hidden contemporaries, and possibly even capture them on camera. After all, the extrasolar world of desire is only 124 light-years away from us. And what's 124 light-years? Well, in astronomical terms, no more than a stone's throw. But for space travel, this distance unfortunately still represents an insurmountable hurdle. A single light year is an inconceivable 9.46 trillion kilometers. And although the two Voyager probes have been flying through space for almost 50 years, they haven't even covered a single light day yet. And that's not because the aging probes are creeping through space like slow snails. In fact, their traveling speed is around 61,500 kilometers per hour. But 61,500 kilometers per hour is simply not enough to make the leap to exoplanets or alien star systems. And that's putting it mildly, because K2-18b is by no means the only celestial body out there suspected of harboring a groundbreaking secret. In fact, astronomers have already identified a whole series of potentially habitable exoplanets in our cosmic neighborhood. And one of them is practically right on our doorstep. Discovered in August 2016 and located in the constellation Centauri, Proxima b is only 4.2 light-years away from us. The planet orbits its autonomous red dwarf, Proxima Centauri, which in turn forms a triple star system with the binary star Alpha Centauri. And since Proxima b is the closest known exoplanet to Earth, it is also the most obvious target when it comes to the question of the research object for the first interstellar mission of all time. The sobering news, however, is that with our current resources, it would take 70,000 to 80,000 years for a probe to reach Proxima b. But in the future, and this is the crucial point, thanks to unprecedented propulsion technology, we could succeed in dramatically shortening this utopian journey time and finally make the dream of interstellar travel a reality. How NASA's Sunbeam propulsion system works. When it comes to speed records, there is currently no way around the Parker Solar Probe. After all, NASA's Icarus recently reached an incredible speed of 692,000 kilometers per hour, flying faster than any other man-made object before it. But let's be honest, what is 692,000 kilometers per hour compared to 100 million kilometers per hour? Well, what at first glance sounds like a crazy speed that can only be achieved in science fiction films is actually the realistic travel speed that NASA is aiming for with its Sunbeam concept. That's equivalent to 30,000 kilometers per second, or about 10% of the speed of light. Against this backdrop, the Alpha Centauri system would no longer be tens of thousands of light years away, but only 40 years. But how on earth is that even possible? Well, basically, the idea behind the Sunbeam drive is astonishingly simple. Instead of providing a space probe with fuel for its journey at launch, it is to be supplied with the necessary energy from outside during its mission. The role of the corresponding permanent filling station is taken over by an external platform, which ensures a constant supply of energy via a particle beam. And let's be clear, The aim is not to send a puny mini-probe to distant stars and planets, but a full-grown 1,000 kilograms research probe equipped with all the latest instruments. The real heart of this innovative propulsion technology is the relativistic electron beam. We are therefore dealing with electrons that are accelerated to almost the speed of light, and thus generate enough power to propel a space probe across interstellar distances. And as mentioned, this is to be achieved with an external platform, more precisely, with a so-called solar stated, which will be stationed near the Sun. There it will hover in place with the help of radiation pressure and solar magnetic fields, and fire the high-energy electron beam at the probe. The solar stated thus transfers the impulse that constantly accelerates the spacecraft, without it having to rely on its own fuel. The longer the beam acts on the probe, the greater the speed boost. But wouldn't the electrons eventually disperse in the vastness of space? After all, they usually have the property of repelling each other. Fortunately, we know of a physical solution to this problem in the form of the pinch effect, which is based on Einstein's time dilation. Put simply, this describes the effect that time appears to pass more slowly from outside a moving system. The example of a moving clock that appears to run slower from the perspective of a stationary observer is often used to illustrate this. Applied to the sunbeam drive, this simply means that time dilation prevents the relativistic electrons from drifting apart, and that the particle beam remains focused, even over ludicrous distances. The advantages over other concepts. If this ambitious idea actually becomes reality, we would be able to venture into interstellar worlds for the first time within a realistic time frame and verify firsthand whether exoplanets live up to their exciting reputation as potential cradles of life. And as mentioned above, this also applies to Proxima b. Although the celestial body probably has a bound rotation and is therefore divided into a cold night side and a hot day side, it orbits within the habitable zone. This zone indicates how far a planet can be from its parent star for water to exist in a permanently liquid form. And in the case of Proxima b, it's conceivable that there is a narrow twilight zone between the two extreme zones where cool water splashes merrily along. However, the whole truth is that we simply do not yet have enough data to say whether this is really the case, and whether life may even have already developed on Proxima b. An interstellar space probe could answer this exciting question on site. And Sunbeam is not the only concept being discussed. However, Breakthrough Starshot is approaching the dream of interstellar travel from a slightly different, not to say smaller angle. Once launched by renowned figures such as Stephen Hawking and Freeman Dyson, this approach is based on a mini-probe the size of a microchip, equipped with a light sail and propelled by a gigantic laser array. In comparison, a single solar stated near the Sun seems much more economical, not to mention the advantages that a full-scale research probe would have over such a tiny probe. But when will it actually happen? When will the first Sunbeam probe leave Earth and set off for Alpha Centauri? The hurdles to realization. Well, unfortunately, we will have to be patient. While Sunbeam appears simple and promising on paper, we are dealing with a completely new propulsion technology that must first be developed from scratch. And that applies not only to the relativistic electron beam itself, but also to the requirement that it must be precisely aligned with a probe across interstellar distances. Even tiny deviations would mean that the beam would miss the spacecraft, and the mission would come to a premature end. In addition, the beam requires more and more energy to remain effective as the distance increases. And since the solar stated is to be stationed near the Sun, we would need materials that can withstand the intense heat and radiation of our source of warmth and life. But at the same time, and this is the exciting part, many of the fundamentals of the novel Sunbeam propulsion system are already in place. In fact, the Large Hadron Collider at CERN can already generate beams with higher energy than would be required for Sunbeam. In addition, the beam guidance systems of modern particle accelerators could also be used for precise guidance in space. And if we think back to the Parker Solar Probe, we see that we have already developed and launched space probes that can survive approaching the Sun unscathed. However, the thermoelectric generators that experts want to use to convert the enormous heat near the Sun into electricity exist only in theory. Currently, there's simply no technology that could make the idea of these extraterrestrial solar power plants a reality. The necessary technology still has to be developed. And apart from the question of financing, this will take time. As a result, even the most optimistic forecasts predict that it will be at least 20 to 30 years before the first Sunbeam prototype can be launched. However, our optimistic forecasts indicate that it will take no more than 20 to 30 seconds before your new subscription can start. Simply click the thumbs up and subscribe now to never miss a new video from us again. We'll see you soon.